Okay, pass it up, guys. Homework is due now. Thanks, Adam. Homework is due. You're just coming in. It's due now. Okay, so it's getting good now. We're getting into vector calculus. So this is the good stuff. Hopefully so the key to succeeding from here on out, we only have 4 days of class left. Yep, today, next Tuesday, and then 1 more week, right? So we're going to do vector calculus in 4 days. The key to it is retaining a lot of what we've done already. So this vector calculus brings together probably 80% of what we've done up to this point. So let's pick up where we left off. So we were talking about regions, a connected region. The idea of a connected region is it's one piece, okay? And then the idea of a simply connected region is it's connected, it's one piece, and it has no holes in it. So, for instance, this is it connected? Is it connected? Yes. It's one piece. Is it simply connected? No, it's got a hole, right? So a simply connected region would just be a full blob, right? A full blob of points. No holes, one piece. That's a simply connected region. Okay, so then we said, what about Green's theorem and pieces that are not simply connected, like the one on the left? Any more homework? It's due now. I'm not going to take it at the end of class. All right, here we go. So let's look at a circle. So this is a kind of review last time. So we said with a circle, we said it's not simply connected, but can we use Green's theorem with it? Can we use Green's theorem? So what we did is we cut it, right? We cut it into 2 pieces. And then each piece now is simply connected, right? So if we summed up the double integral or the single integral, whatever, you know, there's 2 sides. We summed up the 2, then it would be the same as the double integral over the whole region. And so going counterclockwise on both pieces, the line integral will be summing up 8 different pieces. And then we saw that you get the cancellation effect, right? So these two will cancel out, equal and opposite line integrals. These are equal and opposite line integrals. And so then what's left when we add up all those pieces? So we get around counterclockwise around the outside and then clockwise around the inside. Remember, so this orientation of the boundary is such that when you walk on it, the region is always to your left. And so that's consistent, right? If you walk on the outside counterclockwise, the green is to your left. If you walk on the inside clockwise, the green is to your left, right? So basically, so our region is D. And the boundary of the region then is made up of 2 pieces, right? So we can't just look at the C1 as the boundary. So using Green's theorems means that C has 2 loops that form the entire boundary of D. So when we use Green's theorem, we've got to consider the whole boundary, which is in 2 pieces now, C1 and C2. All right, so here's Green's theorem. So your line integral for Green's theorem then is split up between the sum of the 2, the C1 line integral and the C2 line integral, and that's what equals now the double integral over the region. Okay, so then what does that mean in a conservative vector field? If you're in a conservative vector field, what do we know about this? What's going to be true? So both sides of Green's theorem are 0, right? In a conservative vector field, we know that every loop is 0. So this needs to be, that'll be 0, and that'll be 0 because in a conservative vector field those are equal, right? That's 0 because it's a closed loop. That's 0 because conservative vector field means those are equal. So then what happens? So then 0 equals the sum of those two, C1 plus C2. And so those C1 plus C2 then have to be equal and opposite values in their line integral in order for them to sum up to 0. Does it make sense? That means that just the line integral C1, either they're both 0, which is unlikely. C1 is going to be non-zero, okay? So this is the takeaway, that if you're in a conservative vector field and you have this non-simply connected region, if you take the integral around the boundary, that will not be 0 because the sum of these two has to be 0, equal and opposite. Does it make sense? Okay, so that brings us back to this problem. Remember this problem at the beginning of class last time. I gave you a vector field like this, and we checked that it was conservative. We got that qx equals py, right? And then we did this square path, and as expected, around the square path was 0. And then we did the circular path, fully expecting that that line integral would be 0, but it was 2 pi. So now we know why it's 2 pi, and when put it together, why is it not 0? That's what I just told. What's that? So when you do this, he's saying there's a hole present. When you do this around the unit circle, is what's inside simply connected? Is what's inside simply connected? Mark? What's that? What's going on at the origin? Look at the vector field. Not defined at the origin. That's what Seth was saying too. There's a hole in this vector field. It's small, but it's a hole. So what's happening? It's like the example I showed you on the previous page. We're doing this loop around the outside, but then there's a little hole in there, and there's so it's this vector field is kind of when you go around the origin, you get a region that's not simply connected because there's a hole. So how could we remedy that? We could. So if we actually want to see how Green's theorem actually gives us a 0 circulation, then we need another path in here. So now that will have some finite radius, right? So do another path, and that's going to go which direction? Clockwise. So this one's clockwise. This one's counterclockwise. So we could and say that that has radius equal to r. And so if I were to parameterize a little circle with radius r centered at the origin, it would be, so this would be, so we'll call this C2 outer. And now we have a C2 inner. And how do I parameterize C2 inner? So r, right? It's going to be now r cosine theta, r sine theta. And what's that? Oh yeah, good point. Good point. Yep, we're going clockwise now, so it'd be negative, right? The y's are going to be opposite what they would be if you went counterclockwise, so it'd be negative r sine theta. And if we do the line integral over this one, C2 inner of what? F dot dr you should be able to predict what we would get. We should get negative 2 pi, right? We should get negative 2 pi because, and then now that would be, this would also be, we would, as we do that integral, then we're going to take the limit as big R goes to 0, right? So we need to get everything except the origin. So we're going to take the limit of that integral as big R goes to 0. Of this. And when you do that, now Green's theorem kind of checks out because now we have a region. It's not simply connected, but we've considered the whole boundary of this kind of donut with the infinitely small middle, right? We've got the outer boundary and inner boundary. And so the sum of those two integrals, 2 pi, you get 2 pi going this way, and then the itty bitty circle going around this way will give negative 2 pi. And so you can do the math, right? So when you set up this line integral, actually the reason it ends up being negative 2 pi is all the big R's will cancel out. All the big R's will go away, so the limit as R goes to 0 is just the same as what you get when you do the integral, because the R's go away. And you get negative 2 pi, and it still works. So any path that you take that doesn't contain the origin, like the square, you can say, well, it's conservative within that because it's actually a conservative field within there because it's a simply connected region. But any path you take that contains the origin on the inside results in a region that's not simply connected, and you've got to consider the whole boundary, which means make a little boundary around the hole, and do what we did on the previous slide. Okay, does this make sense? Okay, so moving on to new stuff. So Green's theorem is done. In recitation, the last question on web work was a little more challenging, and so you'll in web work today. He'll go over that one. If you were in web work Tuesday, or in recitation Tuesday, he had an example similar to that last one. So probably, I would guess the people who had recitation Tuesday had higher success on that problem. So he'll go over that with you today, that last problem on web work. Okay, so that's Green's theorem. And that's our second fundamental theorem, right? We have the fundamental theorem of line integrals. And that was your homework for web work for Tuesday, and you did some of that in your written work. And then so Green's theorem is our second version of the fundamental theorem. And we got 2 more to go. The fun ones. Can I erase and go on? All right, so the next thing we have to talk about is curl, understanding curl. So if you have a vector field F, we want to talk about what does it mean, what's the rate of change. So a vector field F is just a special kind of function, right? It's a function whose independent entity is location, and the dependent entity is what if it's a vector field? So given a location, a vector field function gives you a vector, right? So that's the idea of a vector field. So as a function, it has a rate of change. In fact, it has 2 different kinds of rate of change. The first rate of change that a vector field has is called curl. So what we want to do is, we want to look at, say, a region in the xy plane there, D, and we want to focus on, investigate just one element of that, okay? So investigate a small element, dA, of the region D in this vector field. And the vector field we're going to define as our standard PQ, right? P is a function of x and y, and Q is a function of x and y. So we're going to blow this up, meaning make it larger, not destroy it. Okay? So we're going to blow this up, and there's our little element. So its dimensions are dx by dy. And that's one little element of our region D. Okay, and that is what? That's in a vector field, right? So we can think about what are the vectors just on the outside of that, or at the edges of that. So I'm calling that F top, FT, F bottom, F right, and F left. So we're zooming in on one little element, and we're examining the vector field at that element. And I'm saying that there's just to the left, what's the vector just to the left, or at the left edge? And what's the vector at the top, the bottom, the right edge? Okay? So if we're talking about rotational rate of change, we want to define what's going to be positive. What's going to be positive rate of change? So what would make sense? What's consistent with what we've done before? We're talking about rotational. What would be positive? Counterclockwise, right? So according to the right-hand rule, right? So we want counterclockwise rotation is going to be our positive rate of change. In other words, the curl will be greater than 0. Okay, so what components of these vectors, so we're going to isolate the components of these vectors that contribute to rotation at this element. So, for instance, if I look at this bottom one and I take this component, which component is this? So what do we call that? No, but what are we calling the x component of f? P, right? So this is P, B, right? This is P for the bottom vector. And I'm going to do that for the top vector as well. So that's PT. So do you see that PB and PT are going to try and rotate around this thing, right? Because so it's you're pulling on this element in this direction. If you pull on the bottom and the top laterally, it has a rotational effect on that spot. Does that make sense? You should see that, right? What about the vertical components of FB and FT? Do they have a rotational effect on it? Pushing up and down here, or pushing down, up or down here. No rotational effect, right? The rotational effect from the top and the bottom vectors are going to come from the horizontal, right? That's what's going to cause this thing to rotate. Okay, so what we're going to do is we're going to look at the change in P. So as we change Y, as we get a little change in Y here going up, we're going to look at the change in the P vector. So as we do a little change in Y, how would we, and we want the resulting change in P. So the resulting change in P is like what? PT minus PB. And we can, because we're in a very small, we're talking about a differential of area, we can call that dP, right? dP. So what would the rotational rate of change be, right? What would the multiplier be on our change in Y to give us that change in P? Right? This is the idea of rate of change. Given a change in independent, given a change in Y, dP would be the rate of change times dy. So what would the rate of change be? Okay, so what? Q is going to be our vertical component, so it won't have to do with Q. So what rate of change times a little change in Y will give us the resulting change in P? Okay, it's the partial of P with respect to Y. It's if you took the partial of your p with respect to y, that would be your rate of change, your constant rate of change that given any change in y would give you the corresponding change in p. This is just dy equals mdx, right? We talked about that earlier in the semester. What's the meaning of the rate of change? Given any change in x, the change in y is the rate times that change in x. Well, that's exactly what we have here. So we've got a little change in y. We're talking about the constant rate that will give you the corresponding change in p. Okay, similarly, going from left to right, I'm going to look at what component is going to contribute to rotation here. Which component of this vector will contribute to rotation around this element? The vertical, q, right? So this is like this. So it's ql. And the vertical this. qr. So what do I want? For a change in x, I want to know what the resulting change in q is. What's that rate of change associated with, given a change in x, you want the change in q. So you can all get that now. What will the rate of change be? Partial of q with respect to x, right? Okay, so now a positive rate of change of p with respect to y. Does that cause counterclockwise rotation or clockwise rotation? If, the way I'm showing it, right, so that pt is greater than pb, does that cause clockwise rotation or counterclockwise rotation? Clockwise, you see that? But curl, we want positive is going to be what? Counterclockwise. So what's going to be the contribution to the curl? Is it going to be the partial of p with respect to y? It's going to be... No, both of these are contributing to rotation. So both are contributing to rotation. It's just that when partial of p with respect to y is positive, that's clockwise, and we want to kind of figure out what the total counterclockwise rotation is. So what will the contribution be from the p's? Negative. We'll have to take the opposite of it, right? But what about the q's? So an increase in q for a positive increase in x, does that contribute to counterclockwise rotation or clockwise? That's counterclockwise. So the contribution from partial of q with respect to x will be positive. Does it make sense? So we're going to take the positive partial of q with respect to x, because positive means counterclockwise, but for p, positive would mean clockwise, and so we're going to take the opposite of that. And we're summing those up to get the total rotational rate. That should look familiar, right? What is that? Right, in Green's theorem, we did the double integral of that, right? And that's what? That's the rotational rate of change at every element, right? So this is the rotational rate of change at every element times a little bit of area. It's like summing up all the rotational accumulation within the region. So that's why the qx minus py is a rate of change. It's the rotational rate of change, right? It's taking into account the horizontal components of the vectors above and below, and the vertical components on the sides, which all contribute to rotation, and adding them together. So this is what we mean by the curl of f. This is the curl of f. It's the rotational rate of change. So in my diagram, looking at the lengths of these vectors, if it's all to scale, do you think the overall rotation is going to be positive or negative? So what about the contribution from the p's? This is resulting in negative curl or positive curl? Negative curl, right? Counterclockwise. And the q's? Positive. So we just have to eyeball which wins, right? Based on the length of these vectors, Which has a bigger differential, right? Maybe Q. So maybe the overall effect here is a little bit of a positive curl or positive rotating rate. Okay. What if they balance each other out? What if these were equal? It wouldn't rotate, right? So if the differential of P was equal the same as this differential of Q, then they would be fighting and they would balance each other out, and that would be when these are equal. And what kind of field would we have? We'd have a conservative vector field, and so that's why conservative vector fields are called irrotational. At every point in a conservative vector field, there's zero rotation because these are equal. These cancel each other out. Just kind of almost like this picture is showing, right? Almost like this picture is showing. But you guys voted on Q winning, right? So if Q wins, then it's not irrotational. You have a little bit, at this point, you have a little bit of counterclockwise rotation. Okay, but actually the curl of F is rate of change, but curl of F is actually a vector. It's actually a vector. So if we're talking about counterclockwise rotation, what is the direction of it as a vector then? What's that? Positive z, right? So right-hand rule. Counterclockwise, going around in the xy plane this way, means that this thing has a direction in the z direction. So as a vector, it's the magnitude times k, right? The direction in the positive z unit basis vector. Okay, anybody have a question so far? Yeah, please. So that's what this is showing, because do you see that the vector here at the bottom has a smaller, that one's smaller than this, right? So when you put those together, the net effect is like this vector, the change would be like this one minus this one. So dp would be like some maybe vector like this at the top. If you did that minus that, you'd have like this much left, right? So dp would be equivalent to having just zero down here and a little bit this way at the top. And so what way is that going to spin it? It's going to go that way. So you have a bigger tug on the top going to the right than you have on the bottom going to the left. So that the one on the top is going to win. It's going to turn this way. So and that's a positive partial of p with respect to y, right? But as a contribution to counterclockwise rotation, then we need the opposite of it, right? Yeah. So Q then, same thing from here to here. The differential in Q is bigger on the right. So dq you could draw it just on the right, like a little vector like that. How much ever this one is bigger than this one. So positive partial of Q with respect to x is what I'm showing an example of that. Causes counterclockwise rotation, so we just take the positive version of it as the contribution to the curl. Make sense? All right, so that's curl in the xy plane. So in the xy plane, then, you really mostly just talk about its magnitude, which is this. Because you're not really dealing with the z-axis. If you're in like Green's theorem, right? If you're in the xy plane, everything's happening in the xy plane. So you normally talk about the curl just as the magnitude. But the reason I bring up that it's a vector is that curl in R3 is kind of, instead of having a little, think of it as a little dy dx, now you have like a little cube, and you have 3 rotations contributing to the curl, right? Parallel to the xy plane, this one, parallel to the yz plane, and parallel to the xz plane. So you have 3 different, because your vector's in 3D, there's 3 different things, each of those having its own 2 things like this contributing to the curl, right? So in each plane, you're going to have something like that contributing to the curl. All right, so let's look at the YZ plane. So now so imagine that this is now, we actually now have a solid, we'll call it solid E. So this is 3-dimensional. And this is actually 3-dimensional. And that would be what, dx. But we don't really care about dx. So now what we care about is just rotation parallel to the yz plane, or the curl that would give you, by the right hand rule, a positive x, be in the positive x direction. So everything's the same, right? So now this is our q, right? So this is, I'm sorry, so the vector field then is PQR now. We have a 3-dimensional vector field. So these vectors have 3 dimensions, but all we care about is the y and z dimension of them. So for instance, this one down here is going to be what? What is that now? That's q. That's the y component of this 3-dimensional vector. And then this is that's the z component of that 3-dimensional vector. It also has an x component. We don't care about that in terms of rotation parallel to the yz plane. So then, for a change in z, we're looking at the change in q, right? Sorry, I just called these q and r before, right? So this is q sub b and r sub b, right? Is that consistent with what I did before? Yeah. So it's the same thing. So the yz plane is exactly like the xy plane, but now our y is horizontal and z is vertical. Our horizontal components of the vectors are q, and our vertical components are r. So given a change in z, we want to know what the change in q is. And that's going to be according to the rate of parcel of q with respect to z. And just like before, the positive version, when that's positive, that's going to make clockwise rotation, so we need the opposite of that. We need the opposite of that as its contribution to curl, right? And then, same thing, change in r. The change in r resulting from the change in, that should say, it should be, is this right? Yeah, change in y, that's right. So this, I don't really need the red one down there. I need the red one here, right? This is my, what? R sub L and R sub R. So again, the partial of r with respect to y, when it's positive, it's going to cause counterclockwise rotation, so we're going to just take the positive contribution of that. And so then what do we get? It's totally analogous to what we had before. Yeah, it would be partial of r with respect to y minus partial of q with respect to z. So as part of the curl vector, it would be times what? I, right? It's going to be I, right? Because YZ, counterclockwise, by your thumb is going to be the, we're talking about rotation around the x-axis or parallel to the YZ plane. So what operation does all this have to do with? That from first couple weeks of class, yeah. Yeah, this is about cross product, right? Cross product is all about the right-hand rule, and it's like we're crossing. It's like we're crossing this change in y with our the dr, right? Because those are perpendicular to each other. The change in y that we have and the change in r are perpendicular, and so we're crossing those to get the rate. So there's a, and remember how we found cross products? We used the 3x3 matrix. So we can do that here. Oh, there we go. I had it. Just didn't push the button enough. There it is. We already wrote that. So this is the x-axis rotational rate, right? Is be r sub y, or partial of r with respect to y, minus partial of q with respect to z. So what we can do is this is about cross product. So we can use this kind of cross product algorithm to generate what the curl is. And so we're going to do the same way, but we're just going to put our unit basis vectors in the first line, and then the operators of taking the partial with respect to x, taking the partial with respect to y, taking the partial with respect to z in the second row, and then our components of our vector field p, q, and r. So it's not these aren't, so the second row is not, they're not mathematical quantities, they're operators. So it's kind of stretching a bit, right? It's not really a 3x3 matrix of all vectors or magnitudes. That second row is signifying do this operation. So for instance, what did we say our xy plane rotation or around the z-axis was? So look, so we're going to go what? Down to the right, down to the right and add, down to the left and subtract. So when you go down to the right and add, you get the partial of q with respect to x minus the partial of p with respect to y. There it is. You see? So we got ux minus py times k. And what's the one that we just did? We just did around the x-axis, right? So what would that be? Partial of y with respect to r minus, going this way, partial of z with respect to q. So going down this side like that, that's positive, right? Remember our cross product algorithm for doing the cross? Finding the determinant of a 3x3. So we're using that algorithm, but now multiplication means do an operation, right? That's what that second row is. These the partial derivative operators. So that's r with respect to ry minus, yeah, qz. Is that what we found on the previous slide? And so the last one, we won't do the geometry of it. We'll just write it down now by this. Okay, so it's gonna be plus black. So now j, right? So it's gonna be partial of p with respect to z. So going down this way, right? Minus r with respect to x. And that's the curl. It's a vector that signifies, what's its magnitude? Its magnitude would mean what? Magnitude of the curl? So the magnitude of the curl would have what meaning? How fast it's rotating, right? It's rotational rate of change. Rotational rate of change. That's the magnitude. And what's the direction? Yeah, but so this is going to be a three-dimensional vector, right? So at a given point in space, in your three-dimensional vector field, at a given point, your curl is going to be a vector like this. The magnitude of that vector is the rotational rate of change at that point. What would the direction of that vector give you then? By the right-hand rule, it would so the plane that's orthogonal to that would be the direction of rotation in that at that spot, right? Because the direction of rotation could be like in 3D, it could be like on any plane in there, right? So you imagine, so if the curl vector is like that, then at that point, your rotation is spinning into that plane. When you do the contributions of all the three coordinate planes, right? So you've got contributions from all three directions, and when you sum all those up, when you take and compile those all together, you're going to have some rotation in some direction, and that's going to be according to the right-hand rule, and that the direction of the curl is going to point orthogonal to the plane of rotation at that point. Orthogonal to plane of rotation. Why? Because if you have a combination of rotation parallel to the three coordinate planes, put that all together and it's going to be at some skew plane, right? It's going to be some angle plane to the axes, maybe, right? Okay. Does it make sense? All right, so then the other type of rate of change is called a divergence. It's a lot easier. It's super easy. We'll do it in 5 minutes. Get the hard one out of the way first. Any questions on curl? So divergence is like the expansion rate of change of f at a point. Again, we're going to look at our little elements. We're going to start in the xy plane, but actually, yeah, that's almost the same xyz. All right, so looking at, say, the bottom and top vectors, what components of those are going to contribute to expansion or contraction at that point? So again, we got PQ, right? So I've got P of B and Q of B. We're back on the xy plane again. So we got P and Q. PT and QT. What components, so now talking about at the top and the bottom vector and the top vector around this little element, what's going to contribute to expansion or compression or contraction? Which component? Q, should make sense. Q, right? If P is going to have to do with rotating this thing, right? Q is just pushing or pulling on it, not rotating it, just pushing or pulling on it. Okay? So, given this particular setup, I got, which is bigger, QB or QT? So then is the overall effect going to be expansion or contraction? This would be like compression or contraction, right? Because the overall effect would be like a small vector down here pushing in this way, right? Okay, so this is looking at a change in, for a change in y, what your change in q is. So this is the partial of q with respect to y. And which component is q of the vector? X component? Y component, right? P is the X component, Q is the Y component. So look, you take the Y, it's so easy, right? You take the Y component of the vector and take its partial with respect to Y. So the change in the amount of Y in the Y direction is going to give you an amount of either stretching, expansion, or compression, contraction. And then what about X? In the X direction, we want which component? We're going to focus on the P component in the X direction. And then we're going to focus on what? If we now talk about R3. Partial of R with respect to Z. Now, does compression or expansion have a direction associated with it? Just so if we think in R3 now, think in R3, you've got a point in your vector field, and you're going to calculate either the overall effect of, it's going to end up being an overall effect of squeezing or an overall effect of spreading out. Is there a direction to that? There's no direction to that. So this is not a vector. Divergence is a scalar. So this is a scalar rate of change, no direction. And so look, we want the, we're looking at a differential in the direction of dy, and we're looking at a differential of vectors in the direction of dx. What operation is that? When you want what? So we want the contribution of this in as much as it's in the direction of that. So we want the contribution of these vectors in as much as they're in the direction of y. This is dot product, right? So now our dot product is going to be this gradient operator dot f. And so we can set up a vector. No, so sorry. So it's not a cross product anymore. It's just partial with respect to x vector. So you make your operators into a vector like this. Partial operators. Dot PQR. And it's like falling out of bed, doing the dot product. We want in the direction of x, we want the partial of p with respect to x. And then what are we going to do? We're going to add the partial of q with respect to y and add the partial of r with respect to z. So all you do, since it's just, there's no direction to it, you just add up the three contributions from the three different directions of either stretching or compressing. And that's called the divergence of f. Again, it's a scalar. It's not a vector. Just like dot product gives a scalar, right? Dot product gives a scalar. Cross product gives a vector. So in a vector field now, there's two rates of change. There's rotational rate of change, which is the curl, which is a cross product kind of entity. And then there's the divergence, which is expansion or contraction rate of change. At what rate is this thing expanding out or contracting? Okay, and that's a scalar, right? That doesn't have a direction associated with it. You just sum up the contributions from the three components.
These aren't for that area. These are for the vector field itself. It goes which way the vectors are kind of turning as you go along.
It's how the vectors, curl is how the vectors tend to turn a small element. And the divergence is how the vectors tend to either, kind of pull outward on it or push inward on it. So two different rates of change in a vector field. Yes, please. It's because of what we're taking, right? So here we want, with respect to y, to get compression. So for a change in y is this direction. Which components are we going to take to get compression or expansion? The y. We want to look at this, right? We want to look at this associated with a change. So how much does q change with respect to y? It's going to tell us how much we're either pushing in or pulling out. Because for a change in y, we were looking at for this change in y, for curl, we were looking at the horizontal components of these vectors were causing rotation. Right? So vertically, the vertical vectors cause expansion and contraction on that element. But vertically, the horizontal vectors cause rotation. Was there another hand? Yeah, please.
I was just going to ask, like with planetary stuff in mind, would expansion be caused by possibly like the sun pulling on the Earth? Could the Earth be expanded? So gravity.
If you had a force field, there's a gravity force field, then yeah, your divergence would be, your rate of change would be the amount of the pull. Yeah, like how much is pulls. So that would all evolved in planetary physics. Okay, so let's look at some examples. So start with this one. Here's a vector field. So, is the curl positive or negative? Is the curl positive or negative? Positive, because the whole thing's rotating counterclockwise. All right, let's look a little closer here. So, let's look, say, right about here. So, I'll do black and blue here, so black. So looking at these horizontal components going up, are those getting bigger or smaller? Smaller. Is that indicating clockwise rotation or counterclockwise rotation? Say at that point right there. At that point right there. If this vector is larger than this one, is larger than this one. Okay, don't go there. Okay? Just tell me, is it clockwise or counterclockwise rotation according to the fact that these vectors get smaller as you go up? Clockwise. All right, let's look at vertical. I'll do blue. So going this way, these are getting what? Bigger or smaller? Smaller. So say right there. Does that indicate clockwise or counterclockwise rotation? Clockwise. What's the curl? Positive or negative? It's negative. Both of those together give us this kind of rotation. Why? Because curl is it a global phenomenon? What is curl? Curl is a function, right? A function of what? Location, right? It's not a global phenomenon of a vector field. It's given any point in your vector field. Given any point in your vector field, what is the rotation at that point? So like right here, we just showed that it's here, even though the whole thing is like a whirlpool turning counterclockwise, at any given point, you have clockwise rotation. So imagine if this is like a water field and you put a little flywheel in there. So don't confuse how the flywheel's going to move with how it's going to spin, right? How it's going to move is which way? It's going to move like all the way around here. But as it's, what we just found is, as it's moving, what's it going to do? It's going to spin clockwise, and that's what the curl is. Curl is a local phenomenon. So as this thing moves around this way with the streamlines, it's going to rotate this way. Curl is negative. Curl is negative. All right, another example. Oops. What about this one? What's the curl? Positive. Why positive? You haven't learned your lesson, right? What's the curl? Who knows? Who knows? You can see that globally it's turning this way. So what I want you to do is I'm going to tell you what this vector field is. It is negative y over x squared, 1 over x, 0. So I want you to find the curl algebraically. I want you to find the curl algebraically. So P is so you can use that algorithm that I So rather than using the result, I think what's easier than using like the result and trying to plug everything in is just do the matrix. Just build the matrix and do the matrix. I think that's maybe a little easier. So you can do IJK. And then you do operator with respect to, don't have a lot of room, so I'm just going to do it this way. Operator with respect to z. And then you put in your vector field in the last row. So negative y, x to the minus 2, x to the minus 1, and 0. And then just work out the cross product algorithm, but you're not multiplying. Okay, partial of y with respect to 0. So we'll do the x component of the curl first. Partial of y with respect to 0. Partial of z with respect to a function of x. So taking the partial derivative of z of 1 over x, which is 0, right? Partial of z with respect to a function of y and x. 0. Partial of x with respect to 0. 0. Okay, last but not least. And so, and in an R2 vector field, that's what we'll always, if we're in R2, this is always going to be the case. Your curl in the x and y directions is going to be 0, because we're only talking about x, y. Really? So this is really, in the xy plane, this is just really about qx minus py, which is our last thing here. Partial of x with respect to x to the minus 1. Negative 1 over x squared. Partial of y with respect to negative y over x squared. Same thing, but subtract. So minus negative 1 over x squared. Curl is 0. Conclusion? Curl is 0. Conclusion about the vector field? Conservative vector field. Conservative vector fields are irrotational. At any point in the vector field, so you put the flywheel, going to put the flywheel on this one, what's going to happen? Right, it's not going to spin. Anywhere. No matter where you put the flywheel in there, it will move around the streamlines. It will move in a big counterclockwise loop, but it will not spin. It will never spin anywhere in there. So this vector field is conservative, and because it's conservative, it's irrotational. There's at any point there's no rotation. All right, so let's calculate the divergence of this. Let's do it. What's the divergence of this field? The divergence of F would be partial of this one with respect to x. Would be, I think, 2yx to the minus 3. Because you're going to have a negative. The negatives will cancel out. Negative 2 times negative 1. So 2y over x cubed. Partial of this one with respect to y is 0. It's a function of x. There is no y. And of course 0. Oh, it's not a vector. What are we going to do? Don't make a vector. Instead, we add. So the divergence is non-zero. So I think the answer to your question is no. The conservative really relates to the rotational rate of change. Okay, so what does this mean that the divergence is 2y over x cubed? So what does it mean that it's this function of y and x? The fact that the divergence is a function of y and x means what? Exactly. So if I'm at the point 1, 1, the amount of divergence is 2. And is that 2 away from the origin like this? No, it's a local phenomenon, right? So like curl, it's just at that point, the tendency of the vectors right around that point is a rate of change of 2, expansion of 2. All right, what about over here at, say, negative 1, positive 1? Negative 2, right? So at that point, there's a tendency for contraction at a rate of negative 2, etc. So then, like negative 1, negative 1s can be positive. 1, negative 1 will be negative. So it depends on, so the magnitude and whether it's contraction or expansion is dependent on your location, right? So it's a function. So the divergence is a function, just like curl is a function. But this is a scalar function versus a vector function, right? Divergence is a scalar function, meaning given any point, you're just going to get a number. And that number, if it's positive, it indicates an expanding rate. If it's negative, a contracting rate. So divergence and curl are functions. Just like back in Calc 1, your derivative, your rate of change is a function of your x value. So now divergence and curl, the rotational rate, the expansion rate is a function of where you are. It's a function of what location you're at. Okay, so now this worksheet is practice in this regard, and I wanted to take some time to do it, but we kind of got to start one last thing before the end of class. So I'm going to leave this to you, but you're going to do what I did on that previous example. You're going to look at this example here. So I picked a point up here, remember? And I said, what's happening to the horizontal vectors as we move vertically? To look at curl, right? To look at curl. As you move vertically, horizontal vectors are decreasing, and that would indicate clockwise rotation. But then you have a component in the other way too, so we looked at what's happening to the vertical components as you move to the right. That would indicate what? Also clockwise rotation. And so because it's indicating clockwise in both directions, you can definitively say that the curl is clockwise. So that's kind of the process you're going through in working through these. So you're trying to say, is the curl positive everywhere? Is the curl negative everywhere? Or does it depend on the location? Or is it zero everywhere? You're doing your best to kind of put that together. And then, like we've done before, you're going to determine what the vector fields are and work the curl and the divergence out algebraically to check your result of your guess about the curl and the divergence. Does that worksheet make sense? So you should definitely work that out over the weekend, and maybe on Tuesday we can just take 5 minutes and pick one of those four and go over it. All right. So then divergence would just, in this example, divergence would be the same thing. So let's predict the divergence here on this one. So going up, these vectors are doing what? Getting smaller, right? Which would indicate compression, right? Compression. And going to the right, these vectors are getting smaller. So what would we say for the divergence? Negative, right? It's both in both directions. It's indicating negative. That as you go this way, it's compressing. As you go to the right, you have compression as well. So I think we said so the curl would be negative and the divergence would be negative. Say at that point. So then you want to do it for several points to see if you can make some kind of overall conclusions about the whole field. Okay. What's that? Oh. Yeah, you're right. You're absolutely right.
Stretching horizontally, compressing vertically.
Yeah, so what's going on here? So the this minus this it's the okay, so it's the change in this. It's the change in this from here to here. So is that change positive or negative? So this is more negative, less negative. So that's a positive change. Right. So for a change in x, dp is actually greater than 0 because this is a larger negative vector than this one is. And so these vectors are getting less negative, which means dp is greater than 0 for dx. So that is in this direction. In the x direction, you have a positive contribution to the divergence. In this direction, you have a negative because those vectors are getting less positive. So there's a canceling effect, and our best guess would be that the divergence is 0. But we don't know, right? So because we're just eyeballing this. Okay? In the x direction, you've got positive divergence. In the y direction, negative. So maybe our best guess is divergence is 0. Okay, yeah, good point. Okay. So we have 3 minutes. I think it'd be better if we see if you can try one of these. So let's do one that's a little different here. How about so let's do the one on the lower left. Try that. predict if the curl is positive, negative, 0, or dependent on location, and predict whether the divergence is positive, negative, or 0. Maybe we've made a conclusion about the curl. Positive, negative, or 0, or different depending on location. So here, curl is no negative, clockwise, right? So bigger at the top and smaller at the bottom must be clockwise. That's the same thing over here too, no matter where you pick. What about down here? Bigger at the bottom left than at the top would also be that. So everyone see that this is negative curl everywhere. It's clockwise rotation everywhere. No, it wouldn't, because on the like this axis right here, because above you have a little bit this way, and below you have a little bit this way. So it's still turning that way. See that? If you go up a little bit, just above it, it's going to be a little bit that way, and below it's a little bit that way. So the curl is negative everywhere. Okay, what about divergence? Up and down. So there's no y component to these vectors. It's all 0. And what about left and right? Equal on both sides, right? So get at any y value, the x vector, it stays the same. The x component stays the same. So divergence is 0. And so this is so let's just confirm that. This is the vector field, what, y, 0. So qx minus py is, what's qx? 0 minus py is, nope, 1 equals, the curl is -1 everywhere. So this is a constant curl. No matter what your location is, you have the same curl of -1. Divergence. Partial with respect to x, 0. Partial with respect to y, 0. That's what we said. Divergence is 0. So this is incompressible. Divergence of 0 means incompressible. That's the word. So we got irrotational is 0 curl. Incompressible is 0 divergence. So actually,